Hey everybody, Dr. White here with a little discussion on the negative binomial distribution. First of all, I want to introduce you to a concept that we've been kind of gravitating towards over the last few sessions, the concept of a Bernoulli process. A Bernoulli process is just a sequence of Bernoulli trials, all with the same chance of success P, and with no fixed end to these trials. Just keep trying again and again and again. And all the trials are independent. Now, for some fixed integer r bigger than 0, let's let x be the number of trials until the rth success. Oh, that's too bad the way the PDF scanner works. I was really hoping for be able to make nice blocks. Oh, too bad. So anyway, what we're doing here is we are waiting until the rth success. We're not counting how many successes we have. We are waiting until the rth success and counting how many trials it takes to get all the way to that rth success. So I think of this as a waiting random variable, as opposed to a counting random variable like a binomial random variable. In fact, we've got 4 random variables up now that it's worth kind of comparing. So where I'm circling here, we've got 2 counting random variables. Bernoulli, which is focused on just one fixed trial, and you count whether or not you got a success, 1, 0. You got binomial, where you have some fixed set of trials in mind, n of them, and you count how many successes are in those trials. Those are counting random variables. But you've also got weighting random variables. We've met the geometric random variables where you're waiting for your first trial, okay? Waiting for your first success. And then, kind of corresponding to the binomials, we've got negative binomial random variables just now introduced. And there you're waiting for your rth success. So, Bernoulli's are a special case of binomials where the number of trials is just 1. Geometrics are a special case of negative binomials where the number of successes you're waiting for is just 1. So keep in mind special case, general case in this table, and keep in mind counting versus waiting. We're going to extend this table as time goes on and we learn about more families of random variables. So we'd like to know what's the probability that our capital X negative binomial is equal to little x? What's the chance that it takes little x trials to accumulate the r successes? So focus in on this picture here where I'm waving the mouse. Each of these little lines is basically standing for a trial, and we could fill in over the line how the trial turned out. S for success, F for failure, maybe. And, what if it is X trials for your rth success? Then there would be X of these little boxes here, one for every trial. And the very last one would have to be a success. That's when you get your rth success, and then you stop watching the Bernoulli process. But that means that you need r minus 1 successes sitting in these boxes right here. And that's x minus 1 boxes, okay? The rest will be F's for failures. So how many ways can you take X trials to get the rth success? Well, it would turn out to be the number of ways to fill in these x minus 1 boxes with r minus 1 s's, and the rest are failures. So you think to yourself, oh, this is the number of ways to pick r minus 1 of those boxes to have the s in them. The rest will have f. So you're looking at x minus 1 choose r minus 1 ways to do this. And when you do it, there'll be r minus 1 successes in those x minus 1 in those x minus 1 boxes. And the rest, which is x minus 1 minus r minus 1, is going to be failures. Now, let's think about for any one of those ways, what's the probability that it happens exactly that way? Well, I argue that it's got to be this, because you're going to have r minus 1 successes in the first x minus 1, and you'll have x minus 1 minus r minus 1 failures in the first x minus 1 spaces. And then you've got that success sitting in the last space, so chance of success p for that. And of course, that simplifies down to, see if I can make this. No, it just separates them out. How sad. Very sad. P to the r times 1 minus p to the x minus r. Okay. So if all of the ways have that same probability, and there's x minus 1 choose r minus 1 ways, then you can see that the probability mass function is just going to be x minus 1 choose r minus 1 times p to the r times 1 minus p to the x minus 1 minus r minus 1, which simplifies down to just that x minus r that you see there. So that's good for any x that's at least r, okay? You can't do it, and you can't get r successes in less than r tries. Now, something I'd like you to notice about negative binomial random variables, thinking back to Bernoulli process, let's define x1 to be the number of trials to get to your first success. And then let's let x2 be the number of trials, additional trials, to get to the second success. So if like you get your first success at trial 3 and your second success at trial 7, that was 4 additional trials to the second success. Similarly, x3 is going to be the number of additional trials to get to the third success, and so on forever. So for example, if this was the way the Bernoulli process started out, then the x1 would have to be 1. The x2 would have to be 4 because of this. The x3 would have to be 2 because of this, and so on. Now, I claim that for every I, xi has a geometric distribution with chance p success. Because within each interval where you're waiting for that success, that's a geometric random variable. Also, since all the trials are independent, the xi's are independent. You know, if I'm like waiting around for my fourth success, it doesn't matter how long I had to wait for my first 3. It's just like I've started over and I'm waiting for a success, you know. So all these xi's are independent of each other. And the negative binomial random variable x, number of trials until the rth success, would actually have to be the sum of the x1 up to the xr. So very important lesson to think about here. A negative binomial RP random variable is a sum of r independent geometric p random variables. That's kind of in line with what we learned earlier about binomials. A binomial in P is the sum of n Bernoulli P's, and they're independent too of each other, you know? Now, in line with what happened with binomials, where the expected value of a binomial was n times P, that's n times the expected value of a Bernoulli, and the variance of binomials was n times p times 1 minus p, which was n times the variance of a Bernoulli, you might expect something similar for negative binomials related to geometric. And in fact, that is true. the expected value of a negative binomial turns out to be r times the expected value of geometric, r times 1 over p. And the variance works the same way. So r times the 1 minus p over p squared variance for geometrics. That really does work. This kind of analysis, breaking up into sums, I can't make it mathematically rigorous at this point because it involves some theorems about expected values and when you are working with more than one random variable at once. And we really don't cover that topic until like way into chapter 4. So I don't have a totally airtight argument here. I've just got this intuition. But if you want to see the airtight argument that involves, the usual summation types of calculations, then just look at the textbook. They also, in the textbook, derive the moment generating function for a negative binomial. And lo and behold, it turns out to be the moment generating function for a geometric raised to the rth power, the number of successes you're waiting for. Just like with a binomial random variable, its MGF was the MGF for Bernoulli raised to the nth power, the number of trials. So something's obviously going on there, some general fact we're seeing instances of, and we'll have to dig into that eventually. So here's a little cartoon of me thinking about digging into that eventually. So let's try some examples. How about example 5 in this section? Say that you keep rolling a fair 6-sided die until you've seen every side at least once. So that could be a while, right? The first time you roll it, you've seen a new side, like maybe you see the 4. And the next time you roll it, you're looking for something other than the 4. And now there's only 5 things that are new out of the 6 possibility. You're still likely to see something new on the next roll, but maybe you will or you won't. I mean, you keep on going until you've seen all 6 different faces land up. And let's let x here be the number of rolls needed until this happens. What's the expected value of x? So again, the book is kind of slipping in, dealing with multiple random variables at once without really telling you that it's not equipped to do so. That's okay. Let's follow up on this. The suggestion is to write x as the sum of 6 random variables, where xi, for I goes from 1 to 6, is the number of additional rolls you need until you see a new face. So like x1 is how many rolls you got to take until you see a new face when you haven't even started yet. Well, we know that x1 is just going to be a constant random variable. It's going to be 1 all the time. But what about x2 here? The number of additional rolls till you see something that you, other than the one thing you've already seen. Well, as we pointed out in our previous remarks, there's a 5/6 chance each time of rolling something new. You're just waiting for something new. So x2 is a geometric with parameter 5/6. Sorry, there's a cat in the background knocking things off of the edges of things. How about x3? So you're looking for your third new thing. You've seen 2 different things already, so you only have a 4 in 6 chance each time to see that new thing, but you're waiting for it, geometric again. And similar geometric all the way down the line until you're looking for the last new thing. And so only one of the 6 faces is what you haven't seen, so you have a 1 in 6 chance each time. So if we make this not mathematically proven assumption that the expected value of a sum is the sum of expected values for different random variables, then we just add up the formula for expected values of geometrics, and we get, well, the expected value of 1 is 1. And for the others, the expected value, remember, is 1 over p, and so we have the reciprocals of all of our success probabilities there. We could simplify that, but I don't care to. So that's a pretty cool thought, really. I like that. Of course, you can do computations with negative binomials with R, so we should take a look at that in a second screencast. For now, that's all, and I'll see you soon.